We're back in the workshop today. EE488, day 11. We're starting on transformers today. I have everything set up. Here's the setup I'll be using today. We're going to start with this. This is a transformer core. It's made of iron. It's a very high quality iron for use as a transformer. And we're going to start the demonstration with that. I have the two pieces of iron here and I'm going to work with them. This is called a CI core. You have one that's in the shape of a C, one that's in the shape of an I. And when we use it as a transformer, we'll actually fasten those together. In production, they would be glued together, pressed together very tightly so there would be no air gap between the two. Today, I'm not going to actually operate this transformer, but when you do the first Transformers lab, you will be using these same cores and you will wind a transformer on them, put them together, and test them. I'll start with the C part, and I have a piece of wire here to demonstrate with. This is a copper wire. It has an enamel insulation on it, so the insulation is a coating. It's a very tough coating. To actually use the wire, you have to get some of the insulation off the end, and to do that you either use an abrasive sandpaper or you use a flame to burn it off. I'm going to wind this on the C part of the core, so I'll just wind it around here. So there's 1, 2, 3, 4, 5, 6, 7, 8. I have 8 turns on that core. I have a fairly short piece of wire here. It's not a practical transformer that I've wound, but to wind a practical transformer, I'd need to put at least 100 turns on there. It still wouldn't operate very well. That's what you'll do in the lab, though. But you don't want to watch me put 100 turns on this today. So I'll set that one down. That's one winding. Here's the other part of the core. I'm going to do these as 2 separate parts. So I will wind another wire around this one. There's 1, 2, 3, 4, 5, 6, 7, and that's all the wire I have. I cut 2 very short pieces. 7 turns on the secondary, 8 turns on the primary. You may have made an electromagnet at some point in your life. If you scrape the insulation off this wire and connect it to a battery, then this would be a magnet. That's important for the operation of the transformer. I have 2 pieces of the iron core here. If I connect these together, that is a transformer. Here's my drawing of that transformer. I have in blue the iron core. I have in red the turns I put on one side. I have said it has N1 turns on that side, and I'm calling that the primary winding. In green, I have the turns I put on the transformer on the second side. I'm calling that the secondary winding, and I'm saying that has N2 turns. If I connect a source to either side, I'm going to put it on the primary side. I called it the primary side because it was the side I was going to connect the voltage source to. Call that voltage source V1, the primary side voltage. When I energize that source, it will set up a magnetic flux in the core. And I'm going to show the flux flowing from left to right here. That's actually using the right-hand rule on the red winding. If the voltage is positive at the top, negative underneath, if you use the right-hand rule, then our convention says the magnetic flux is flowing out the top of that winding. So there's the magnetic flux. We use the Greek letter phi for that. That magnetic flux is flowing in the iron core, and it links with the other coil, and it causes a voltage to be induced on that secondary coil. and that is V2. Faraday's law defines the voltage that is induced on a coil of wire. Faraday's law says E equals minus N d phi dt. E is electromotive force. EMF. That's what the E's for. It's an archaic term for voltage, but we use it when we're talking about a voltage that's induced. So E is equal to N, number of turns, d phi dt, time rate of change of flux. And there's a minus sign in there that tells you the polarity of the voltage that is induced. If you have a time varying flux flowing through a coil of wire, even if it's just one turn of wire, there is a voltage induced. And that's what Faraday's law tells us, and that's how a transformer works. The coil that is energized sets up the flux in the core by Faraday's law. The coil that is not energized has a voltage induced on it. The minus sign on Faraday's law tells us the polarity if we pay attention to the direction of the windings. In an actual transformer, we just mark the polarity of the transformer on the transformer itself. And that's what the two blue dots are on the transformer that I've shown. So the dot convention is the dot convention that we use in engineering. You may have learned this differently in physics, but this is how it's done in electrical engineering. The dot convention, voltage is positive R positive at the dots. So if you have a transformer that's not marked, you need to find out the polarity of that transformer. And the way to do that is connect it, use an oscilloscope, and see what the polarity is once you energize the primary, and mark it yourself. This is an experimental technique. You can also do it by looking at the direction of the turns if you can get inside the transformer and see the turns, but usually you can't do that. So it's almost always done experimentally. Voltages are positive at the dots. Primary current is into the dot. So we'll define the current I1 going into the dot on the primary. Secondary current is out of the dot. So we'll define I2 as out of the dot. The other way to look at that is using passive sign convention, and we are assuming that power is going into the dot on the primary, and we're assuming that power is coming out of the dot on the secondary. This is convention. If you label it wrong, if you're not sure which is primary, which is secondary, because you can't always see that on a transformer, you'll get a negative value somewhere, or you'll get the wrong phase angle, and you'll know that you labeled it wrong. Let's use this to look at transformer theory. I just copied the diagram from the first part, and we're going to use that to define some equations for an ideal transformer. So I'm assuming here that this is an ideal transformer. So let's label it that way. In an ideal transformer, the voltages and the currents are related by the ratio of the number of turns on each coil. The voltage equation is V1 over V2 is equal to N1 over N2. The current is related by the inverse of that. I1 over I2 equals N2 over N1. This is a passive device. Ideally, it does not consume any power. There is no power source so that can add power to the output. So power in is power out, and we can write that as equations. V1 I1 conjugate is equal to V2 I2 conjugate. So complex power in is equal to complex power out. Real power in is equal to real power out. Reactive power in is equal to reactive power out. Power factor is the same on both sides. That's an ideal transformer. Let's look at an actual transformer that I have connected here. Now we're back to the setup on the workbench where we have an actual transformer connected to a source and a load. This is the transformer. There are 3 of these transformers mounted on this board so that I can do 3-phase demonstrations with it. The transformer is rated 120 volts on its primary side and 7.2 volts on its secondary side. Those are 60 hertz ratings. The transformer also has a power rating of 20 volt amps. We'll talk about what those mean in just a moment. The voltmeter and the ammeter on the left side are the source primary side. The voltmeter and the ammeter on the right side are the secondary side. In the back is a space heater. This is a mostly resistive load. It does have a small motor powering the fan. I'm operating this 120 volt heater at about 7 volts, so the fan is not going to come on. So we're going to have a mostly resistive load connected here, and it's a 1,000 watt heater, so it's a fairly large load, which means fairly small resistance. It's enough to let us do the demonstration on this transformer. So that's connected on the secondary side. I'm going to energize the whole thing through the outlet strip, and I'm going to take these readings. So what I have is open circuit. You'll be able to see all of these in a moment. At open circuit, primary voltage is 122. Secondary voltage is 7.1. So V1 magnitude, 122 volts, rounding off. V2 magnitude is 7.1 volts. Secondary current is reading very close to 0. It's reading actually 1 milliamp, and that is noise in that last digit. We can't trust that. I'm going to turn on the load. I'm not going to leave it on very long because it's hard on that motor to be energized when it's not turning. So, with load, we have primary voltage 122, secondary voltage 6.2. Interesting, the voltage has dropped significantly on the secondary when I turned on the load. Secondary current is no longer 0. It's reading 698, 697, so we will call that 700 milliamps or 0.7 amps. That's all I need. I'm going to come back to the primary reading, but for now we're going to just use the secondary values to calculate primary values. Here's the data. At the top are the ratings for the transformer I have connected. Let's look at what those ratings mean to start with. 20 volt amperes, that's the one I want to look at. Power rating. It has units of volt amperes, so it's either complex or apparent power. And because there is no imaginary part or phase angle on it, it's apparent power. The power rating is 20 volt amperes. This means the current rating for the primary side current rating is 120 volts. The voltage rating, the power rating, 20 volt amps over 120 volts. That's the primary current rating, 0.17 amps. That's assuming there's a decimal point after that. Primary current rating. Secondary current rating. Same power rating. That allows us to calculate the current ratings on both sides. I2 rated is still 20 volt amps over 7.2 volts. Much higher, 2.8 amps. And those are different by the turns ratio. What is the turns ratio? Let's go to the data. Here's my data. Scroll down to that. Because I want to calculate now I1. And I said above I1 over I2 is equal to N2 over N1. Let's use that. Calculate I1. So I1 equals I2 times N2 over N1. Another way I can write that, because I can't get into that transformer and count the number of turns on those windings, there are hundreds of turns on both of those windings. I can tell you because that's what's needed to make a transformer work. So I do this. I say I2 times V2 over V1. Now, which V2, V1 do I use? I have three choices. I have the rating, so I can use 120 volts, 7.2 volts. I have open circuit values. I have V1, V2 open circuit, and then I have values when the transformer's loaded. Which ones do I use? There's no absolutely correct answer on this. You do not use the loaded values because we're going to come up with a different way to calculate those loaded values. But we use either the rated values or the open circuit. If I haven't done an open circuit test on the transformer, I don't have those, and I use the ratings. If I have done an open circuit test on the transformer, that's what I use because I think it's going to be more accurate than using the ratings. The primary side current for this transformer, if it's ideal, will be I2, 0.7 amps, times open circuit values. Let's write this out. This is what I'm doing. I2 times V open circuit 2 over V open circuit 1. So 0.7 amps times 7.1 volts over 122 volts, which gives me a value of 0.058 amps or 58 milliamps on the primary. 700 milliamps on the secondary, 58 milliamps on the primary. the voltage is higher on the primary, the current is lower on the primary because the power is the same on the primary and the secondary, at least in an ideal transformer. Let's do one more thing with the data we collected. Let's calculate the resistance of that space heater. To calculate the resistance, it's connected on the secondary. R2 will equal, by Ohm's law, V2 over I2. We are assuming it is a purely resistive load. V2 under load was 6.2 volts. I2 under load was 0.7 amps. And that gives me a resistance of 8.9 ohms. Let's do that calculation on the primary. R1 is equal to V1 under load over I1 under load. V1 I measured, and V1 under load was 122 volts. I1 under load I calculated as 0.058 amps. And when I do the calculation on that, I'm going to see that I have a much higher resistance appearing on the primary. It's not really there. It's connected on the secondary. 2100 ohms. Those two resistances are actually related by the turns ratio. I can write the ideal transformer formula as this. The resistance that appears on the primary, it's not actually there. It's connected on the secondary, but if I take the ratio of voltage to current on the primary, I will get the ratio of voltage to current on the secondary, the actual resistance that's connected on the secondary, multiplied by the turns ratio squared. So that means if I multiply the R2 value by, let's write the formula first, V1 over V2, square that, that will give me the resistance that appears on the primary side. Because in our case, V1 is much higher than V2, the resistance that appears on the primary side is much higher than the resistance that appears on the secondary side. If I actually do this calculation, it doesn't come out the same. I get 89 ohms times 122 volts over 7.1 volts. Make sure I have the turns ratio correct. That does not give me 2100. It gives me 2600. Why? Is what I've told you completely wrong? No. This is the ideal transformer equation. Our transformer is not ideal. You may have noticed that when I was doing the measurements, which I will show you again, the primary current also was not what we calculated. We calculated a primary current under load of 58 milliamps. Let's see what it actually is. Looking at the actual transformer as it is set up, I have the space heater turned off, so there's no load on the circuit. I energize the circuit, and I have About 7.1 volts on the secondary, about 122 volts on the primary, so the same as they were before. Current on the secondary is reading 1 milliamp. We know that's zero because it's open circuit. There could be some leakage there. Primary current should be zero. If this is an ideal transformer, if there's no current on the secondary, there's no current on the primary. We've got 77 milliamps on the primary. Let's energize the space heater. Now we have about 700 milliamps flowing on the secondary, and we have 95 milliamps flowing on the primary. We should have had 58 milliamps flowing on the primary. Why do we have so much more? Because this is not an ideal transformer. We'll get into those non-ideal properties of transformers on another day. For today, we're going to stick with the theory of ideal transformers. There is another example completely worked out and posted on the web page. So that is it for today. We'll take a look at the homework assignment next.